We'll go ahead and get started with the hands-on portion. So I can share these slides later. What Dr. Gaur is going to do is share a zip file containing some examples. You can download that and do the simulations as we go along. Okay. So we are going to use lamps. I think we've already installed, many of you have already installed it. If you've not done so, you can try to do it in a few minutes. And there are some examples, but we will also install a visualization tool called as OV2. Okay. It's a very good tool for not just visualization, but also calculating several properties that we'll be interested in. The examples that I wanted to show, first thing is melting of argon. I think you already had an example on argon, is that right? Okay, were you able to run this example? Yes or no? Argon. Was there an example on argon covered already? Okay, so we'll run this and we'll also visualize the structure. We'll see how we can characterize the liquid phase and the solid phase of argon. And we look at the tensile behavior of copper. Yeah. Oh, okay. One second. Can you see it now? Okay. So we'll install lamps in OV2. Following that, we'll look at the phase transitions in argon by using a very simple pair potential called Ranganathan's potential. And the second example will be the tensile deformation of copper. And here we will see how the potential that we use will affect the results. Okay. We'll use two different potentials. One is called as Morse potential. The second one is called as the embedded atom potential, EAM potential. And finally, we will look at diffusion of polymer chains. We will try to calculate the diffusion constants from tracking the trajectory of all these polymer chains. Okay. So LAMPS, as you may already be aware, is a very large-scale molecular dynamics tool developed by Sandia National Labs in the US. And it was originally developed as a classical MD code, but now people are adding more and more functionality. There are a lot of additional packages that people have built into LAMPS. It's completely open source, so you can look at the source code if you want. You can modify it if you want. It's written in C++. And it's primarily a particle-based simulation. So let's say atoms and molecules easily simulate. And you can simulate it either using a single processor, which is what we're going to do today, or if you have access to parallel machines. These days, all laptops are multi-core laptops. So most likely you already have a quad-core or 8-core machine, or even more if you get latest laptops. So it's possible to run this code even using parallel setup, okay, what is called as MPI. We won't go into the details today, but there are several help files that are out there if you want to run it in parallel. And these days, people are talking about mixed architecture or hybrid architecture using GPU, OpenMP, and other packages. And the advantage is you can couple this MD simulations with several other simulation strategies like quantum mechanics, Monte Carlo, finite elements, etc. We won't go into those details today. As I showed you some examples, it's very versatile in nature. You can simulate a lot of different materials. It's very well documented. So as long as you have patience to read the description online, you can get to know about all the functionalities and eventually, of course, implement these models for your research, right? But the underlying thing is have patience. Okay, and it's possible to extend this as well. So let's say some functionality is not there, and if you are ready to get your hands dirty and modify the code, you can do that. It takes a lot of effort, but you can do that. This is the LAMPS website. Maybe you've already seen it. It has links for downloading it, various tools and other information. Of course, this is a scripting tool, so which means that once you have an executable, you need to write a LAMPS script to actually perform your simulation. You of course need to have a starting structure and other potential definitions, etc. We will go through those examples later on. And eventually this LAMP script will instruct the executable to perform the simulation. Okay? And the output will typically be some data. Okay? You can either visualize the trajectory or calculate some information from the trajectory. And we'll see those examples for the three cases that we have. Okay, so how many of you have not been able to install LAMPS so far? Okay, 1, 2. Rest all of you have already installed LAMPS? Okay. I think initially I had passed on an instruction to install Ubuntu or some Linux like emulator for Windows. But later on I figured that it's possible to just download a ready-made executable for Windows. So if you've not installed it, I encourage you to go to this website, docs.lamps.org/install_windows.html. Or if you just Google LAMPS Windows install or something like that, you'll get this link. In fact, let me do that as we speak. Okay, so this is how that link looks like. We go to this link and yeah, you see something called as 64-bit Windows download. I'm assuming most of you have 64-bit. In case you have 32-bit, there is a different file for that also. Once you click there, it will take you to several packages, but you can download this one called LAMPS 64-bit latest.exe. Okay. Just let me know if you're unable to find it. Yeah, sure. No, it is just the distance in whatever units LAMPS is computing. So if you use units like real or metal, the distances are computed in angstroms. Right? So whatever data you have will be in angstroms. But if you use units called as LJ, then it will be in units of sigma. Right? Does that answer your question? Yeah. Correct. Lattice size. It doesn't matter because whatever distances you're getting, these are just pair separation distances. Right? So if it is crystal, then you will obviously see peaks in your RDF that correspond to those specific lattice spacings. Right? So yeah, in some sense, once you plot the RDF, you will know whether it has a lattice structure or not. Right? But this is an average quantity. So if you have, let's say, 1,000 atoms, it is an average over all those 1,000 atoms. Right? So that in crystals, for instance, you will have first nearest neighbor, second nearest neighbors, etc. Right? So you get all those peaks. Correct. Yeah. If it is a liquid, it will have short range order but no long range order. If it is gas, again it will have some short range order, very limited short range order, and then it will have no long range order. So you'll just see a small hump, and then it will be a flat line. Okay. Are you able to download this exe file? Okay. So if you double click that, it'll ask you if you want to install it. Just click yes. It will take maybe 1 or 2 minutes to install. So people who are joining online, please let me know if you have any difficulties. Okay, can I move ahead? You've installed it? So if you have used Ubuntu to install it, it's slightly different. But what I'm showing is using Windows, okay? Just a Windows installer. Very similar. In case you have any difficulties, we can discuss. So once the installation is complete, you need to open the command prompt. Just type CMD from your start menu. You open up a window like this. Okay. And once you have extracted the file that you downloaded containing the examples, you can go to that particular folder, use the cd command to go to that folder. So those files are there in my downloads folder. So initially, if you command prompt window, by default, I'm in C:/user/admin. So I can go to cd downloads. Okay, and my folder is inside this. So the way you go there is by typing cd space the folder name, and if you're using Linux, then you need to use /. If you're using Windows command prompt, you need to use / to go to a different folder. Okay, this folder is in folders here. And to see what are the files there, you can type dir. Okay, people using Linux, what is the command that you use? ls. Yeah. Okay, so these are the 3 folders: argon_lg_melt, deep spring polymer, copper_tension, cu_tension. Okay. I'll go into the first example. Okay. The input file is called in.argon. So let's take a brief look at what it contains. So this is the screenshot of the entire script. You can use any text editor like Notepad or WordPad to open this and see. So what we are simulating is 3-dimensional Lennard-Jones system, okay, and the system is argon. And if you look at the input script, you can you can see several commands. Okay, each of these commands are LAMPS commands that have various roles that it plays. So let's go through it quickly. We want to define a set of units for our system first of all. So, for instance, yeah. Okay, we'll come to that in just a minute. But meanwhile, you can open the script and just go along the script. The first thing is the units command. We want to define what are the units that we will use. So for the argon system, we are using a system of units called metal. Okay. So it will mean that let's say distances, pressure, temperature, and other properties will be measured using some standard units. Okay. And if you want to know what units these are, you can go to the LAMPS help page and go to the metal units page. It will tell you what are the various units for various quantities. Okay. And the second command is the atoms type. Here again, you have various settings. So our system is argon. Okay. It's just atomic argon. So all the atoms of argon are just atoms. We are not having any bonds or molecules of argon, right? Unlike in materials like polymers. Okay. So that is our atoms type. And then we are using periodic boundary conditions along all the three axes. Okay. Does anyone not know what are periodic boundary conditions? You don't know? Okay. So give me 1 second. Okay, so periodic boundary conditions are perhaps the most important set of conditions that you need to use in MD simulations. Imagine you have a room filled with air molecules, right? So the number of molecules are of the order of Avogadro number, right? Naturally, we cannot simulate such a large system. So what we'll do is simulate a much smaller subset of such atoms, typically few thousands to few millions, let's say. But we will use what are called as periodic boundaries. Okay. So what that means is, let's say you're tracking the movement of some molecule. Okay. Yeah, you can pay attention. Right? You're following it, right? Okay. So let's say you're following the movement of some molecule in the simulation cell. Okay. It is going from left to right. And then finally, it's going to hit your simulation wall. Okay. But the system is actually bulk. It's infinitely large. And the way you do it is by building what are called as periodic boundary conditions. So whenever the atoms exit from the right side of your simulation cell, it will come back from the left side. Okay. And likewise along the two other axes also. And the way you do it is by taking into account what's called as the minimum image criteria. You don't have to know a lot about this, but internally LAMPS is doing this. Okay, so imagine this is your simulation cell. Okay. The middle cell is your simulation cell. It has, let's say, 4 atoms. What LAMPS is creating internally is it is creating a multiple set of copies of that simulation cell. This is just in 2 dimensions, but imagine the actual simulation is 3 dimensions, right? So when, let's say, this atom exits from the simulation cell, okay, its periodic image is over here, or along the left. So that will enter the simulation cell, right? So let's say this particular atom is going down. Okay, so its periodic image is over here. So let's say this is going down. Then this atom will enter from the top side. Okay, so there is no effect of your simulation wall, so to speak. You're not limited by your simulation size. Okay, so this atom can be diffusing for multiple times. You can go from left to right, come back here, again undergo diffusion, the same simulation cell. And it is like, this molecule is actually diffusing in free space if it has an infinite size. Okay, this is very important because just by using a small set of atoms, you can simulate a bulk property. Bulk meaning theoretically infinite large system size. Okay, and think of this as Schrodinger's cat in a box. Right? If your box size is very small, okay, you're going to see your own periodic image, which is going to give you wrong interactions. So you should ensure that your simulation box is long enough so that the effect of periodicity that you're artificially putting in your system is not present. Okay, so this is important criteria. So I encourage you to read more on this. It's a very simple picture that I gave you. But our systems are periodic in this sense. Okay. All right. So we are using periodic boundary conditions along all the three axes, X, Y, and Z. And then our starting structure is going to be an FCC lattice with a lattice spacing of 3.65 angstroms. This is the standard lattice spacing for argon, solid argon. Okay. And we are creating 5 unit cells along X, Y, and Z dimensions. So 0 to 5 represents the number of unit cells along X. Again, 0 to 5 along Y and 0 to 5 along Z. Okay. So 0 refers to the starting value along the next coordinate, 5 refers to the ending value. There are 5 unit cells of argon that we are building in FCC unit cell. We are creating a box and we are assigning the mass of argon, which is around 40 mass units. Okay. So now we want to initialize the velocities as well. So always remember, in any MD simulation, your initial conditions typically include the positions and the velocities. Okay. Positions are assigned here because these are FCC lattice positions, and now the velocities are also assigned. There's a command called velocity that will assign a random set of velocities that will follow some distribution. So we are initializing the velocity such that the temperature of the system is 30 Kelvin. Okay. Can someone tell me why temperature and velocities are related? 3 by 2 kT. KT is equal to half mv square. Okay. So this comes from the equipartition theorem, Boltzmann's equipartition theorem. So each translation mode has half kT of kinetic energy, and that corresponds to half mv square. Okay, that's a classical kinetic energy term, right? So internally, LAMMPS is going to assign a set of velocities to all these atoms. That overall, when you compute the temperature, it's going to give you 30 Kelvin. Okay, and just for your record, I think the melting point of argon is somewhere around 80 Kelvin, right? At room temperature, argon is of course a gas. But below 80 Kelvin, argon is solid. After 80, this liquid. I think after 120 or 130 becomes gas. Okay. And we are using the Lennard-Jones pair step. That's the most simple potential that people use in MD with some cutoff. Okay. Does anyone know what is the meaning of a cutoff for your interaction parameter? Okay. Okay. So you remember how the Lennard-Jones curve looks like, right? It has a repulsive term and an attractive term. The attractive term is not a long-range term. Beyond, let's say, 8 or 9 angstrom, the energy basically goes to 0. The atoms no longer interact. Okay. So it doesn't make sense for us to compute pair interactions for atoms that are more than 8 or 10 angstroms. Okay. So if we're using a cutoff, that means that whenever a pair of atoms are more than this distance, here we have given it as 8.5, LAMMPS will just assume that these atoms are not interacting. And you will see that this is a very valid assumption that we can make, okay? Because it's a short range interaction, right? And finally, we assign the pair coefficients. This is the epsilon and sigma parameter for your model. Okay, the first term is epsilon and the second term is sigma. Okay, epsilon is in units of I think kilocalories per mole for metal units, and sigma is in terms of angstroms. It is 3.4 angstroms. Okay, and then we use a command called neighbor. This is just to ensure how many atoms we want in computing the Lagrange potential. I won't go into the details here for lack of time, but if you increase this number, you are basically accounting for more accuracy. Okay? Smaller the number, less will be your accuracy. And then the final important thing is the time step. Okay? You already know how LAMMPS is calculating the positions, accelerations, and velocities. It uses an integrator to integrate Newton's equations of motion. And the most important thing there is the time step. Okay, you don't want the time step to be too large or too small. If it is too large, it will not converge. If it is too small, it will take a lot of time for the simulation to proceed. Okay, so somewhere intermediate you need to choose. It depends on the particular model and the particular system. Right? And then the main mechanism by which LAMPS will evolve the positions and velocities is by this command called fix. Okay? So fix is basically a command that will alter the positions of atoms in the system. And here we use various ensembles. Do you have ideas about NVE, NVT, NPT ensembles? People typically either keep the system size fixed or pressure or the temperature and some combinations thereof. Okay. So here we are using what's called as the NPT ensemble, where we are fixing the pressure, we're fixing the system size, and we are also fixing the temperature. Okay. So you may ask, then why are we using these two temperatures? Okay, 30 Kelvin to 120 Kelvin. We are essentially trying to ramp the temperature from solid like to liquid like behavior. We want to see where the phase transition occurs. We are doing it under conditions of constant pressure. But NPT ensemble, let's say you fix the same temperature at 30 Kelvin or 120 Kelvin, then it will give you an NPT ensemble, a proper NPT ensemble. The temperature will be fixed. Okay? But it's also possible to ramp the temperature from starting value to some ending values. So in this case, we are increasing the temperature from 30 Kelvin to 120 Kelvin. And there is a characteristic damping parameter. Again, you can read about it later. And we also fix the pressure of the simulation. Okay, so the pressure is fixed at, I think, 1 bar here. ISO refers to an isostatic pressure. The pressure is same along X, Y, and Z directions. Okay, and there is a pressure damping parameter here. And the other important command is the dump command. So dump command will basically give us the history of atomic positions as a function of simulation time. Okay. This is the important file for visualizing what is happening to the system. So here, if you look at this command, dump one all. So we want to dump all the atoms. Okay. And this is a particular style of dump where we want to find out what are the X, Y, and Z coordinates of all the atoms. And this is the name of the file, dump.r. Okay. Finally, we want to output some thermodynamic properties, including things like temperature, pressure, volume, or any other property that you may be interested in. And we want to output that with some frequency. Okay. So we want to write the data every 2000 steps here. Likewise, for dump as well, we are dumping out the coordinates every 2000 steps, right? And eventually, we are performing a simulation for 50,000 time steps. It's not a very large number. As you will see, it will take maybe 1 or 2 minutes on your laptop to run. But this is what we're doing. Okay. So whenever LAMPS sees this command called run, it will start doing the integration of motion. Right? You have Newton's equations, and it will keep iterating the solution, okay? Partial differential equations for 50,000 steps. Okay. So finally, how long will your simulation be just from this data? Can someone tell me? No, not the execution time, the time of your simulation. Okay, so the time step here we are using is, by the way, this unit time is measured in picoseconds. Okay, so this is 0.002 picoseconds, which stands for 2 femtoseconds. Okay, typical time step is in this range, 1 to 2 femtoseconds. And the total time that your simulation is run, that will be time step multiplied by the number of steps. Okay. So 50,000 times 2 femtosecond. So how much is it? 500,000? 0.5 nanoseconds? Sorry, one nanosecond, not 10. I don't think it's 10 nanoseconds. Femtos 10 power minus 15, nanos 10 power 9. So it will be 0.1, right? 0.1 nanoseconds. Okay. All right. Okay. So now let's try to run this. Okay. So I've gone to the folder where the input script is there. This is the input script called in.argon. And if you're using a Windows machine, the executable is called LMP. So if you just type LMP, it should be able to load labs automatically. Okay, you can press Ctrl C to escape from there. And the command is LMP minus IN. Okay, minus IN stands for the input file. You want to give this file in.argon. Okay, then press enter. It will start running. So it's outputting the number of steps that have been completed. Okay. You see that it's pretty fast. So are you able to install it? Okay. Is there anyone who is not able to run the example? All right. So you also see how much time the simulation took, 33 seconds in my PC. How much did it take for you? 17. So yours is much faster system than mine. Oh, you ran on parallel. Okay. Okay. Because I have 32 GB RAM. I was wondering if maybe you have much faster than mine. Uh, okay. Okay. This is some i7. Yeah, it's about 3-4 years old, but when I got it, it was 32 GB RAM. Okay, so let's try to see how we can get some information from this. Okay. Uh, so you'll see that there is some amount of time the simulation has taken, right? In my case, it took 33 seconds total wall time. Okay, and you can see all this information by going to the folder. You'll see a file that's called log.labs. Okay. Once you complete the simulation, you will get this file automatically. Okay. This is a log file, which means that it has all the information about the simulation, including the output. Okay. So the first few lines are basically the commands that you put in the system. And then finally, you'll see all this data about the number of steps that the program has completed, what is the temperature, what is the pairwise energy, the molecular energy. In this case, it's 0 because it is considering atomic carbon. The total energy, pressure, and the volume of your simulation. Okay. You can see that the volume is increasing first of all because you're raising the temperature, and then argon is a gas. Okay, it will go from solid to liquid to gas, so the volume naturally increases. Okay. You'll also see this file called dump.argon. Okay, and we will try to visualize this file using OVTIP. Okay. So has everyone installed it already, or you need some time to install it? Installed it? Okay. So again, this is very powerful tool. Okay, you can open it. And there are multiple ways by which you can open this file. You can either go to file, load file, or you can simply drag and drop your dump file over here. Okay. You can rotate the structure to see the symmetry. Okay. We are simulating argon, and the initial structure is FCC crystal lattice. Okay. So if you see this along the 1-1-1 axis, you'll see this nice 6-pole symmetry. Okay. This is 4-pole symmetry along the 1-0-0 planes. Right. So this is your starting structure, and OVTO will automatically load all the frames. Okay. There are 25 frames here. Can someone tell me why there are 25 frames? Okay. Okay, very good. So in our dump command, we asked labs to dump out the data every 2000 steps. Okay, and we are running a total of 50,000 steps. So naturally, there are 25 frames. Each frame corresponds to the coordinates at the end of those 2,000 steps. And you can simply click on the play button to play the animation for you. So you can see that initially it is in solid state at 30 seconds, and from where here it's starting to undergo this phase transition from solid to liquid. Let me know if anyone has not reached this stage yet. So if you want to go one frame at a time, you can click this play button. You can track the movement of particles one at a time. Visualize it and so on. Is this okay? So just let me know if you're able to load it. Is it okay? Loading? Okay. So in your simulation setting, you can choose to set a particle size. Okay. Let's say if I increase it to 1, my particles will appear much bigger. Okay. In molecular dynamics, all these atoms are considered to be point particles. There is no size associated with it, right? It's just interacting with other atoms through the interaction parameters, basically through sigma in this case. Okay. And this particle size is just a convenience for visualization. If you make it 5 or 6 or something, you won't see any information. It's just rendering it with a much larger size. So set it to something that makes sense to you. Be something like 0.5, 0.9. Okay. You can see the structure very clearly. Okay. And this is completely periodic system. So let me show you some nice features. If you go to add modification here, you can try to replicate the system. There's something called replicate. Okay. You click replicate. You can choose how many times you want to replicate the system along X, Y, and Z directions. If I choose 2, 2, and 2 here, I have basically replicated the system 8 times. Okay, 2 times 2 times 2 along the X, Y, and Z directions. Okay, this is again just for visualization purpose. You can try to color code your system. There's an option called color coding. Okay, you can choose what type of system property you want to color code. Okay, so let's say I want to choose an input property this particle identifier. Okay. Each atom has a unique atom ID or a particle identifier, and it will just color code based on that particular number. Okay. If you want to color code it depending on the x coordinate, you can choose part position.x and then click on adjust frame or adjust range. It will automatically color code the particles based on the x coordinate. Okay. So if we're going to around the x direction, you see that it's starting from 0 or 1 all the way up to 16.425. 0 is your starting value along x, and 16.45 is the ending value along x. So imagine how this can be very powerful. So let's say you want to find the forces on atoms or the stresses on atoms. Okay, you can color code these depending on the properties of these atoms. It becomes very useful for seeing what is happening in the. All right, there's something called as slice. Again, if you click on add modification and slice, you can slice the simulation cell along different directions. Okay. In this case, it is along 100. You can choose different planes for viewing the surfaces. This is along 110. Okay. Basically, you can choose whatever plane you want to visualize. This will be very useful if you have a complex material like composite and you want to visualize the structure, the internal structure of your material. Okay. All right. The final thing I wanted to show you in this example is yeah. Final thing is the coordination analysis. So again, if you click on add modification coordination analysis, okay, it will give you what is called as the pair correlation function. Right? Are you able to see this? Please tell yes or no so that I have some confidence that you're following. So people who are joining online, are you able to run these examples? Can you type in the chat window? Okay. All right. So GOFR or the radial distribution function tells you something about the structure. Okay. So I'm sure you might have had some exposure to X-ray diffraction or some structure prediction tools, right? If you have a crystalline system, you know that there is periodicity in your arrangement of atoms, and this will translate to well-defined peaks in your GeoFR. Okay? This is directly related to your X-ray diffraction peaks. It's basically a Fourier transform of your X-ray diffractive mass. Okay, that will give you the pair correlation function. This is at frame number 0 on the starting frame, where there is perfect order. Okay, all the atoms are exactly at their lattice points. If I just go to the next frame, the very next frame, okay, I see that the atom positions have of course changed, and the GeoFR peaks have also broadened. Can someone tell me why that is the case? So people joining online, you can type in chat if you know the answer. So again, the question is, the previous frame, these peaks are very sharp. If I go to next few frames, the peaks are much broader. What do you think? Okay, temperature, yes, that's the right answer. But clustering is a very loose word. I would say no, it doesn't increase. But this change, right? You look at this number, it's about, let's say, half an angstrom or 1 angstrom. Right? The material is undergoing thermal fluctuations. So atoms are vibrating about their equilibrium positions. Okay. So instead of exact lattice positions, now the atoms are vibrating about their lattice positions. So that leads to what is called a peak broadening. Okay. And now if we keep playing the animation, or maybe we can go directly to frame number 15 or 16. So here you can already see that the geopart is showing much different behavior compared to the initial things. Okay. You can see that some atoms have started to go out of their lattice positions. They have started to melt, right? Because the temperature is increasing continuously. Okay. But go to something like this, frame number 24 or 25. The structure is completely liquid. Okay. The system is above its melting point. So the geopart shows a small peak, okay, around the nearest neighbor distance. It's about 4 angstroms. And then it doesn't show any other peak. It's just a flat line of it. Okay. Can someone tell me why the profile is so rough? This doesn't look like a good data, right? You want to publish this data, people will not accept it. Okay, very good. Very good. Yeah. Your system size is small. I think it's about 2000 atoms or so, or maybe even less. And you're just calculating it for one frame. Okay. Typically, when you report data from molecular simulations, you need good statistical averaging. Okay. So imagine you take the structure and equilibrate it for several tens of thousands of steps and average your data across all those frames. You'll get a very smooth profile. Okay, that will give you much more accurate data. And this is important because now you can find out what is the nearest neighbor distance, what is the coordination number. If you take the integral under this curve, this will directly give you the coordination. All right. So, any other questions on this topic? It's very simple, straightforward example. Okay, shall we move ahead? If you keep increasing it further, there'll be a transition from liquid to gas. So there, your pair correlations will still change. It will show for liquid, you will still see some peak in the first nearest neighbor distance. For gas, it will be even lesser. I'll quickly show you how it looks like. Correct. Yeah. So if you're able to average your data very well, then your radial distribution function will look something like this. Your solid will show very defined peaks, just like how you would get in your X-ray diffraction. Liquid will show a first nearest neighbor peak because it has short range order, and then very small peaks at the second nearest neighbor. Whereas gas will just have very small it has very small short range order and no long range order. So typically this is how it will look like. Yeah. So if you know what is the sigma, this is 3.4 or something like that, you can choose to normalize it with sigma. Post processing, yeah. If you use Leonard-Jones unit, there is a units LJ command also that will directly give your separations in terms of sigma. Okay, so that is directly R by sigma. Yeah, we are also using LJ potential here, but units we are using as here metal units. But you can use LJ units also, where sigma and epsilon will just be given as 1. Okay, and whatever you are getting will be in terms of those units. And you can scale it. So you can say 1 sigma is equal to 4 angstroms, 1 epsilon is equal to maybe 5 electron volts. You can directly assign some numbers. That's the power of using LJ units. You can give any value to them. Your simulations will be fine. Okay. All right. So let's go to the second example. We look at a more interesting phenomena called uniaxial extension. So, how many of you have seen tensile tests for any specimen? Let's say for steel or some alloy. Have you seen any tensile deformation? Some YouTube video? Okay. All right, let's see. So this is routinely done in materials testing, where you want to find the strength of any material. Okay, this is called a universal testing machine (UTM), and this is basically your specimen. You're loading it between two grips, and then you will gradually apply tensile deformation. Okay, you can measure the stress and the strain here by using some sophisticated instruments, and yeah, basically start applying the load. And it will give you what is the dependence between stress and strain. Okay? So eventually the material might break to go beyond the load carrying capacity. You can see that it's starting to thin down here for the making, and eventually the material will break. Okay, so this is broken. So from the stress strain data, you can see what is the strength that the material can support and so on. And this example is doing precisely this. Go to this folder, cd space backslash or forward slash if you're using Linux. Go to the copper example, okay? Copper underscore tension. Okay. There are two folders here. Okay. One is called EAM, the second is called Morse. Let's go to the Morse one first. This is again a very simple pair potential, just like Leonard-Jones. They have slightly different terms. You can read about it later, read about Morse potential later. So go to the Morse folder and see the contents there. Okay. It has a file called in.tensile. Right? So I won't repeat these data. It's very similar to the previous example. We are creating initial velocity of 300 Kelvin, okay, close to room temperature. And we are defining the pair style, this Morse, pair coefficients plus one is the Morse potential. And the interesting thing is happening here. Okay. We are using the NPT ensemble, doing the simulation at 300 Kelvin. Okay. And we are defining the pressure along X and Y. Okay. This is constant pressure along X and Y axis, but along Z, we are pulling the material. Okay. We are not controlling the pressure along Z, but instead, what we are doing is we are deforming the material. Okay. There is a different fixed command for that called fix deform. Okay. And we want to deform the material every time step by some amount. Okay. Along the Z axis and with a specific strain rate. Because what is important is how fast you deform the material. Remember the examples we saw in the session before, right? The frequency of deformation governs what is the mechanism of deformation. Okay. We are deforming it with a strain rate that is equal to 10 to the power 10, very high strain rate. We are artificially using a very high strain rate because it will complete faster, okay, within a few minutes, right? And we want to average the data, the stress and the strain data. So there is a command for doing it called fixed AV/time, and we are doing this averaging every 50 time steps and saving the stress and the strain, okay, to a file called stress underscore strain.txt. Right? We are also dumping this file every 500 steps into a file called dump.rs, then running it for 20,000 steps. Okay. So once you go to the Morse folder, you can just use the same command lmp space -n and in.tensile. So to start running, so just run this example. So this will take maybe 3 to 4 minutes. Slightly bigger system. I think this is 4,000. Um, 4,000 atoms. Yeah. Same modulus they should show. Transverse direction. Right. Yeah, it'll change. So if you're very close to zero strain, slightly positive and slightly negative strain, like tension and compression, the stress strain data will still follow the same modulus, but the mechanisms for tension and compression will be different. Because the Leonard-Jones potential, if you see, looks something like this. Around the equilibrium position, the compression will have a much steeper rise in your potential energy, whereas expansion is usually much softer. So as long as you are very close to that equilibrium position, you will get the same data. But if you go to larger strains, you will get deviations. Perfect harmonic potential, you will get same data, correct? Exactly. Yeah. Because most of the potentials are anharmonic. You don't have symmetry between compression and expansion. So is the simulation running for you? So, oh, it finished for you? Okay. So you can visualize the data in Ovito. Dump.atom. Maybe a file dump.atom generated. Yeah, you can open that in Ovito. So by the way, when you do research using molecular dynamics, you will typically run these simulations on some high performance computing cluster or some workstation, right? So you won't be running it on your laptop because it'll be very, very slow. Okay. So all the data will be written there on some remote server, and you have to download the data and visualize and so on. So running it on some cluster will be much faster than running it on your laptop. Okay, so let me open this file. Okay, this is how it looks like. There are 40 frames here, and your starting structure is perfectly ordered, face-centered to the upper. Okay, and play the animation. So it is undergoing a tensor deformation along the z axis. Okay, then you see somewhere that there is some contraction, right? And this is the final structure. So initially it's like this, finally it's like this. Okay. So you can clearly see that the symmetry of atoms have also changed, right? So I'm moving along the y-axis here. This is your coordinate axis. So go to the initial frame, it's like this. Final frame is like this. Okay. Something has happened to the crystal. And if you know some theory, you know that atomic planes will shear past each other when you pull them. And you'll have various defects that are generated, dislocations, and other things. I won't go into the details here, but you clearly see some transformations happening to the crystal structure. Okay. Now you can also look at the stress strain.data, stress strain.txt. Yeah. Mhm. It'll be different. It'll be different. It's likely to be different. I'll just show you one more thing since you are. There are many analysis tools in Ovito itself. So there's something called as dislocation analysis, DXA. So if you click that, it will tell you what are the types of atoms the system has. So all the atoms here are green in color. So green refers to FCC in this case. So 100% FCC. If you go to some other intermediate thing, you can see that some atoms are going away from FCC positions. So slowly they are starting to generate some defects. And you see somewhere here the structure has changed completely. So FCC is only 3%, 3 atoms. Most of them have undergone some other phase transformation. Remove the defect mesh. So intermediate structures, OBTO is not able to characterize it because it's not able to find out if the atom is in FCC position or something like that. It's just characterizing it as other. But if you go further, you can see that again there is a mixture of two phases that are found. There are some red atoms that are HCP phase. There are some green atoms that are FCC. So if we go to this angle, you see that there are some stacking faults that are generated. So arrangement is FCC, HCP, FCC, HCP like that. So these are defects that are generated in the system. So again, this is where visualizations are very powerful. So if you look at the stress strain data, it gives you 3 columns. First column is the time step. Second column is the strain in the material, and the third column is the stress. Okay. And you can plot this data using Python, MATLAB, or whatever programming tool you are comfortable with. I'll just show you how the data looks like. I already did the simulation for the two potentials. You can do the same thing for the EAM potential as well. And this is how the data looks like. Okay. Y-axis is the stress measured in gigapascal, and the x-axis is the strain. And you see that the two potentials give you quite a bit of difference in the stress strain response. Okay. If you're just interested in the linear elastic region, a very small strains, okay, see that the two potentials are giving you almost similar data, similar results. So the modulus basically is your slope of stress versus strain in the elastic region. If you are limited to very small strains, right, it doesn't matter which potential you use. Both of them are going to give you similar data. Okay. But EAM is slightly more computationally expensive compared to most potential. So if you want a more realistic description of metallic systems, then EAM is the way to go. Okay. You can clearly see that the plastic region is under-predicted by the Morse potential, right? And all the defects, etc., will also be different for the two potentials. So you need to be very careful in choosing what potential you use for your material. So this comes from referring to literature extensively, using some experience and so on. Okay, and the data will depend very closely on the potential to be used. Okay, any questions on this? So I encourage you to plot the data and try to find the modulus of this material. Try to compare it with experimentally observed literature values for the Young's modulus. Okay, the slope of this will give you the Young's modulus. Okay, we'll just spend maybe 5 more minutes and wrap it up. Let's quickly look at the third example. This example is for a polymeric system, a melt of polymer chains. The input structure is already prepared and given in this folder. This data is called 100 beats data. If you open that, you'll see that there are 2000 atoms. Now the system is different from the ones that we saw earlier. So the first example was argon. There was no bonds defined between various argon atoms. But now we have polymer chains, and we know polymer atoms are covalently bonded with each other. Okay, so there are polymer bonds, and we are using the bead spring model. I briefly mentioned about this in my first talk. There are some coefficients for the intra-atomic potentials, and there are a set of atoms. All these are positions of atoms. If you go down, be some velocities for atoms, and then finally a section on the various bonds these atoms. Okay. This is important because now LAMMPS knows which atoms are bonded together. This is not arranged in any ascending or descending order. That's completely fine. LAMMPS can handle that. What this means is atom number 1436 and 1437 are bonded, 1076, 1075 are bonded, and so on. Okay. You can also look at this input file. Just go to file, load file, and put the beam strain polymer example. Just load this data. Yeah. Reduce the particle size. Okay. So this is how the polymer system looks like. Okay. This is a dense polymer melt. All the red atoms are polymer atoms, and all the magenta bonds that you see connect all these polymer atoms. Okay. So now you can go to add modification. Go to color coding. Okay. Now in the input property, you can choose molecule identifier. Click on adjust range. So now you can see various molecules. Okay. There are multiple molecules here, and each molecule is given a different color. You can do this very easily. And there's something even more interesting that I'll show you. So if you can open the file and follow along. Okay, go to add modification and go to compute property. Okay, go to add modification, compute property, and in output property, click on transparency. Okay. All right. So you will see a column that says expression. Okay. So here you can give any logical expression for making an atom transparent or opaque. It's extremely powerful to know what is happening in your simulation. So I can type something like particle molecule identifier. Okay. I want to select the second molecule out of this entire mixture. So I can choose this by giving a logical command. Move the bonds. Just give me 1 second. Okay, the molecule identifier, I don't know why it's not working, but let's say you want to make some powerful visualizations. Okay. Let's say I want to find out position. If a position of atom is less than some value, I want to make it transparent. Okay. If it is more than some value, I want to make it opaque. Okay. I can give a logical expression here. Okay. What I put is position dot x less than 5. Okay. The x coordinate of the atom is less than 5 angstroms. I want to make it opaque. Okay. Otherwise, I want to make it transparent. So this can give you very powerful visualizations about what is happening to the structures. Okay. And you can use multiple combinations like this. So let's say the x coordinate should be less than 5 and the z coordinate should be greater than 10. Okay. Just as an example, you can give a logical OR operation, and I can put position dot z greater than 10. Okay. I can show a smaller subsection of these atoms and so on. Okay. These transparency values you can change depending on what you want, how much transparent or how much opaque you want to make it. It's completely transparent. Basically, numbers between 0 and 1, the scaled coordinates. Okay. All right. So this example again you can run. What this example tells you is you're just seeing the movement of polymer chains as a function of time. Okay? You're tracking the movement of all the polymer chains as a function of time. You know that these atoms will diffuse, and from the diffusion, you can find out what's the diffusion constant. You can find out means by displacements. So I encourage you to do this. So finally, you will get a data called MSD. Okay, look something like this. Gives you data for variation of time and variation of mean per displacement. Okay. This displacement is for the center of mass movement of all the polymer chains, and you can plot it as a function of time. Look something like this. Okay, this means per displacement as function of time, and these are scaled units. So here we are using Leonard-Jones system of units. Okay. You are asking, right? So these units are in Leonard-Jones, not waste units. Okay, so we're showing it in terms of tau. And the data here, again, there is not enough statistics. Ideally, we should repeat this multiple number of times and get more reliable data. And from the slope of this means per displacement, you can find out the diffusion constant. So you can build more complex systems and then do these things for various systems and various potentials. Okay. So any questions on this? So LAMPS automatically calculates this for you. If you look at the input script here, we are using a compute command called compute MSD. Okay. There are various commands, various compute commands that LAMPS has. You can calculate a lot of different properties by using these commands. Yeah. Right. Yeah. Yeah. Correct. Right. So the main the main test you need to do is to remove the effect of simulation cell size. So imagine you go from a system size of 2000 all the way to 100,000, right? So somewhere you will see that the results are independent of the system size. You don't have to go to 100,000. Maybe 10,000 is good enough for you, right? It depends on the property you want to measure. So let's say mean square displacement you want to measure. You have multiple sizes from 2000 all the way up to 200,000, right? In steps of some number. So let's say 2000, 10,000, 50,000, 200,000. These are 4 data you have, right? You see that the data is not changing from 10,000 to 50,000. Then you know that, okay, maybe 10,000, slightly more than 10,000 is good enough. And then you can do a finer resolution there. From 10,000 to 50,000, you can have steps of 5,000 and see what size is good enough. Okay. This is something you have to do initially. This is like benchmarking your system. So typically, with experience, you will know what is good enough. So you don't have to repeat it for all the properties. Usually beyond a certain size, you know for sure it's not going to have much impact. So let's say you measure 1 or 2 properties and you don't see much variation. Just use the same for other properties. Otherwise, it will be very, very time consuming to run it again. Yeah. Yeah. Correct. You can do that. So LAMPS has this very powerful crystal structure builder, the lattice command. You can create arbitrarily complex lattice structures. Yeah, you can do that in LAMPS itself, but it's a bit tricky. You need to know exactly what are the basis atoms, right? So let's say if it's a complex ternary alloy, where you have a 3-element basis, each lattice point has 3 atoms, right? So you need to know exactly what are those basis positions. Okay. You can create, there's something called lattice custom option. You can create a custom lattice structure. So just look at that. But if you have some database where you already know the position of atoms, you can convert that to a LAMPS readable format and then use the read data command to read the structure. So both options you can run. Okay. You can do that, yeah. The good thing and the bad thing is that there is no standard procedure. You use whatever works for you, right? So the method that you use, you may find it convenient. Maybe your friend might feel that's very difficult to do, right? So there is no single answer. You have multiple ways by which you can create these input structures. So this polymer data, for instance, there is a tool that comes along with LAMPS. Okay, it's called the chain tool. That can already give you this initial distribution of polymer chains. And then you can equilibrate the structure in LAMPS to create a well-defined structure, then use it further. There are several software that will allow you to create molecules, create composites, and so many other things. Multiple ways. So you have to be attentive to what are the tools out there and read a lot of literature that will give you confidence. Yeah. Correct. Very. So liquid structure, it's very simple actually. You start from solid and just melt it at high temperature. Doesn't matter. You create your structure first. You take a solid, melt it, form a liquid, and then use that as your starting structure for further simulations. So liquid structure is not defined, right? Basically you have to equilibrate the system. So if you just go beyond the melting point, you're starting the liquid structure, it will not be equilibrated because it's not under thermodynamic equilibrium and that at that particular state. So you need to run, let's say, NVT simulation at that particular temperature for a few nanoseconds to equilibrate your liquid structure. and then use that as your input for further simulations. Okay? Or you can also define a random starting position. LAMMPS has this command called, I think in lattice command itself, there is an option called random. Just check that. It can create positions randomly in your simulation set. Yeah. You can use that also. But whatever you do, you should ensure that the system is equilibrated before you measure any property. Otherwise, you're going to get wrong results. Okay. Okay. Any questions from participants joining online? I don't think so. But later on, if you have any questions, feel free to reach out to me. I can respond by email, and we can have further discussions offline. Okay. All right. Thanks a lot. All the best for your research career, research journey, and whichever form you want to use molecular simulations. All right. Take care. Use your language. Sure. No problem. No problem.
You can please take a seat. Yeah. So let us thank Professor Raghavan Ranganathan for this wonderful talk and the hands-on session. We can try the things which he has shared with us. So without taking too much time, can we have a brief concluding session? If anybody from the participants, online or offline, they want to share their feedback or some suggestions for future workshop you want to organize, feel free to share the feedback. I know all of you are waiting to go home, but I want to hold you back for 5 more minutes. Yeah, so it looks at everybody, everything was perfect about the workshop. I can assume that. So thank you very much. Thanks for joining and best wishes.